In this lecture, we are going to present a parallel processing technique called pipelining, which is applicable to a wide range of problems that are partially sequential in nature. This means that a sequence of steps must be undertaken. Hence, pipelining can be used to parallelize sequential code. Certain requirements are necessary for improved performance and will be outlined. Here is the outline. First, we're going to talk about what the pipeline technique is all about, and then we'll look at three types of pipelines, and then the computing platform, and then some example applications. In the pipeline technique, the problem is divided into a series of tasks that have to be completed one after the other. In fact, this is the basis of sequential programming. In pipelining, each task is executed by a separate process or processor, as shown in this figure. We sometimes refer to each pipeline process as a pipeline stage. Each stage contributes to the overall problem and passes on information that is needed for subsequent stages. This parallelism can be viewed of as a form of functional decomposition. The problem is divided into separate functions that must be performed, but in this case, the functions are performed in succession. As we shall see, the input data is often broken up and processed separately. As an example of a sequential program that can be formulated as a pipeline, consider this simple loop which adds all the elements of the array A to an accumulated sum. So we could actually unroll this loop to show sum equals sum plus A sub 0, sum equals sum plus A sub 1, sum equals sum sub A plus 2, and so on. So one pipeline solution would be to have a separate stage for each statement. Here is a picture showing that idea. Each stage accepts the accumulating sum on its input, that is S in, and one element of A sub something, the array, on its input, A, and produces the new accumulating sum on its output, S sub out. So this means that each stage is performing this formula shown in pink. So instead of simple statements, a series of functions can be performed in a pipeline fashion. The frequency filter is a more realistic example in which the problem is divided into a series of functions. This is called functional decomposition. The objective here is to remove specific frequencies, say the frequencies F0, F1, and F2, and F3, and so on, from a digital signal Ft. Here is a picture showing the scenario I just described. The signal could enter the pipeline from the left as shown in this figure, and each stage is responsible for removing one of the frequencies. So as you can see from the diagram, after the first stage F0, the signal will be without the frequency F0. Then after the next stage, the signal will be without frequency F1, and so on. And at the end, you get the filtered signal out. A similar application is to recognize certain frequencies in a signal. In home and professional sound systems, for example, there often is a display showing the specific frequencies in the audio output. Each stage of a pipeline could recognize one frequency and display its amplitude as part of a frequency-amplitude histogram. Given that the problem can be divided into a series of sequential tasks, the pipeline approach can provide increased speed under the following three types of computations. Number one, if more than one instance of the complete problem is to be executed. Number two, if a series of data items must be processed, each requiring multiple operations. Number three, if information to start the next process can be passed forward before the process has completed all of its internal operations. These three solutions are identified as Type 1, Type 2, and Type 3. The Type 1 arrangement is utilized widely in the internal hardware design of computers. It also appears in simulation exercises where many simulation runs must be completed with different parameters to obtain the comparative results. Here is a space-time diagram illustrating this kind of type 1 pipeline. So in this diagram, you can see that each process is assumed to have been given the same time to complete its task. Each time period is one pipeline cycle. Each instance of the problem requires 6 sequential processes P0, P1, P2, P3, P4, and P5. Note that the staircase effect that happens at the beginning. After the staircase effect, one instance of the problem is completed in each pipeline cycle. This same situation can be described by turning the axis on its side, which we will see in the next slide. In this slide, the instances are listed along the vertical axis. This form of diagram is sometimes useful if it is necessary to show information passing from one task instance to another, as would occur in processor pipelines. So with P processes constituting the pipeline and M instances of the problem to execute, the number of pipeline cycles to execute all M instances is given by M plus P minus 1 cycles. The average number of cycles is M plus P minus 1 divided by M cycles, which tends to become 1 cycle per problem if M gets very, very large. So then, in any event, one instance of the problem will be completed in each pipeline cycle after the first P minus 1 cycles. This is called the pipeline latency. So that was type 1. Now let's look at type 2. In type 2, a series of data items must be processed in a sequence. Appears in arithmetic calculations such as multiplying elements of an array where individual elements enter the pipeline as sequential series of numbers. Here is a picture illustrating this kind of type 2. There are, in this example, 10 processes to form the pipeline and 10 elements D0, D1, D2, D3, D4, D5, D6, D7, D8, and D9 to be processed. So with P processes and N data items, the overall execution time is again given by P minus 1 plus N pipeline cycles, assuming these are all equal. Now let's look at type 3. This type is often utilized in parallel programs where there's only one instance of the problem to execute, but each process can pass on information to the next process before it has completed. Here we see a space-time diagram showing that when information can pass from one process to another before the end of the execution of the process, so you see that the next process starts up. So if the number of stages is larger than the number of processes in any pipeline, a group of stages can be assigned to each process, as shown in this picture. Now, of course, the pipeline stages within one process are actually executed sequentially. But you can see how, in the end, you still get some speed up because you get to start the next process before the first process is done. So the end of the program will be shorter than if you had done it completely sequentially. Now, in real life, you very often do not have the same number of processes as you have pipeline stages. So how do we deal with this? Well, the obvious way is to group several stages together for a particular processor. So we see in this particular example, we have one processor taking 4 processes. So processor 0 takes process 0 through 3, and then processor 1 takes process 4 through 7, and finally processor 2 takes process 8 through 11. This kind of thing can be achieved automatically in MPI if you just say dash NP and then give the number of stages that you want the processors to take. But that can be a bit less efficient because then each stage is like completely separate from the other stages, and there is communications overhead. So sometimes if you know exactly what your configuration is, you might hard code in processor 0 will take this many stages and so on. So there are different situations in real life, and you might optimize in different ways. A key requirement for pipelining is the ability to send messages between adjacent processes in the pipeline. This suggests direct communication links between the processors into which adjacent processes are mapped. An ideal interconnection structure is a line or ring structure, such as a line of processes connected to a host system, as shown in the diagram at the bottom of this page. Lines and rings can be embedded into meshes and hypercubes, and so this makes them suitable platforms. The seemingly inflexible line configuration is in fact very convenient for many applications, yet at very low cost. To use pipelining with network computers and computer clusters efficiently requires an interconnection structure that can provide simultaneous transfers between adjacent processes or processors. Most computer clusters employ a switched interconnection structure that allows such transfers. A single shared Ethernet connection would not provide such simultaneous transfers. A little flexibility can be achieved on this matter by locally blocking the sends that are normally used. Then a process can continue with the next operation without waiting for the destination to be ready. Now, let's take a look at some examples of using this kind of pipeline architecture. Okay, for this particular example, let's look at the situation of adding a list of numbers. The problem could use any associative operations on a sequence of numbers. A pipeline solution could have each process in the pipeline add one number to an accumulating sum, as shown in this picture below, where one number is held in each process, p equals n. The partial sum is passed from one process to the next, and each process adds its number to the accumulating sum. So here is the basic algorithm for this process p sub I, where first you receive the accumulated sum from the previous process, and then you add your own number, then you send it to the next process. And this is the case for all of them except for the first one where you only send, and the last one where you receive but you don't send and you just then report it. So an SPMD program could look something like this. We check to see if we are the first process. If we are not, then we receive and then we add. And if we are not the last process, we send it on to the next guy. So the final result is in the last process. Now, if instead of addition, other arithmetic operations could be done. For example, a single number x could be raised to a power by multiplying the input number by x and passing on the result. Hence, a 5-stage pipeline could be used to obtain x to the power of 6. In our general description of pipelines, we show the data being entered into the first process rather than already in the appropriate process. If the input data is entered into the first process, it would be natural to return the result through the last process, as shown in this particular picture. This would be particularly appropriate if the processors were connected in a ring architecture. Now, what about for your typical master-slave organization like we have in MPI? Well, look at this picture here. The number of problems are entered into each process when they are needed by the process. And the first process gets the number before the others. The second process gets its number one cycle later, and so on. So this form of message passing appears in several numeric kind of problems. And so pipelines where the information is entered from both ends simultaneously and two-dimensional structures also are possible. So coming back to our problem of adding numbers, it does not make sense to have one process for each number, because then, say, to add 1,000 numbers, you would need 1,000 slave processes, which is usually not that many are available. So generally, a group of numbers will be added together in each process and the results passed onwards. So such data partitioning is used in most numeric applications to reduce the communications overhead and is assumed in all these examples. So how efficient is this? Well, our first pipeline example is type 1. So it is efficient only if we have more than one instance of the problem to solve. This means that more than one set of numbers to add together, because if you only have one, then you might as well use one processor. So for the analysis of pipelines, it may not be appropriate to consider all the processes as having simultaneous communications and computation phases, because each instance of a problem starts at a different time and ends at a different time. Instead, we will assume that each process performs similar actions in each pipeline cycle. Then we will work out the computation and communication required in a pipeline cycle. So the total execution time, T total, is obtained by using our pipeline formula for the number of cycles multiplied by the time of one cycle. That is, as shown in this pink equation, total equals time for one pipeline cycle times number of cycles. So total equals tcom plus tcom times m plus p minus 1. So this is where m instances of the problem and p pipeline stages, where p is the number of processes. Then the computation and communication time is given by tcomp and tcom respectively, and the average time for computation is given by TA equals T total divided by M. Now let's look at a single number being added at each stage. That is, N is equals to P. So the period of one pipeline cycle will be dictated by the time of one addition and two communications. One communication from the left and one communication to the right. So we'll get this pink equation here, tcomp equals 1, tcom equals 2 times t startup plus t data. And each pipeline cycle, t cycle, requires at least tcom plus tcom. Okay, so this means t cycle equals 2 times t startup plus t data plus 1. So the term t data is the usual time to transfer one data word, and t startup is the communication startup time. And the last process only has one communication, but this may not help because all the processes are allocated the same time period. So if we were to have only one set of numbers, m equals 1, then the total execution time, t total, will be given by t total equals 2 times t startup plus t data plus 1 times n. That means n pipeline cycles, because each process must wait for the preceding process to complete its computation and pass on its result. And you get O of n as the time complexity. Okay, so that was for if you only had one instance of the problem. Well, but really the advantage comes when you have many instances of a problem. So if we have m groups of n numbers to add, then each group results in a separate answer. The time of one pipeline cycle remains the same, but now we have m plus n minus 1 cycles, leading to t total equals 2t startup plus t data plus 1 times n plus n minus 1. So if m gets bigger and bigger, okay, then the average time becomes better and better. It becomes, the t average is t total divided by m, which is approximately t startup plus t data plus 1. That is one pipeline cycle, which is great because then every pipeline cycle you get a new result. Now let us consider data partitioning with each stage processing a group of D numbers. The number of processes is given by P equals N divided by D. So each communication will still transfer one result, but the computation will now require D numbers to be accumulated D minus 1 steps plus the incoming numbers, so that this means that this triangular group of pink equations, tcomp equals D, tcom equals 2t startup plus t data, and t total is 2t startup plus t data plus D times m minus n divided by D minus 1. So this means obviously that as we increase D, the data partition, the impact of the communication on the overall time diminishes. But increasing the data partition decreases the parallelism and often increases the execution time. So therefore, you've got a trade-off here, and you've got to balance what is when you get the biggest bang for your buck. Okay, so there you have it. Okay, now let's look at a type 2 example. Sorting numbers. Well, when we sort numbers, we want to make them in a particular order, right? Increasing or decreasing. And if there is duplicated numbers, you just put them next to each other. So a pipeline solution for sorting is to have the first process, P0, accept the series of numbers, one at a time, store the largest number so far received, and pass onwards all the numbers smaller than the sorted number. If a number received is larger than the currently stored number, it replaces the currently stored number and the original stored number is passed onwards. So each subsequent process performs the same algorithm, storing the largest number so far received. When no more numbers are to be processed, P0 will have the largest number, P1 will have the next number, and so on and so on. Okay, so this algorithm is a parallel version of insertion sort. Okay, the sequential version is akin to placing playing cards in order by moving cards over to insert a card in position. The sequential insertion sort algorithm is only efficient for very small numbers because it's really a O of n squared algorithm. So here you see a picture of what was happening in what I described previously, which is that first you have 4, 3, 1, 2, 5 going in, then the 5 goes into P0 and it gets stuck there, and then the 2 goes past the 5, and then the 1 goes past the 5, and then it goes past the 2. Meanwhile, 3 is going past the 5, and the 1 is gone down there, and 1 has gone to the 3rd slot, and 4 comes in while the 4 goes past the 5, and 2 goes past the 3, and 1, and then simultaneously the 3, and then the 1, and then the 2, and the 1 at the end. So this takes 10 time cycles, which is better than if you were doing it with one processor. So it's better than doing it with one processor because the other processors are doing the comparisons for the next number and so on, whereas instead of everybody being done by the same guy. So the algorithm that's going on here is we have each processor, P sub I, receives the number from the previous guy. So if the current number is bigger, if the new number is bigger than my current number, then I send my current number on. Otherwise, then I just send the new number on to the next process. So if you know how many numbers there are, then how many the ith process needs to accept is known. It means it's n minus I. How many to pass onward is also known. It is given by n minus I minus 1, since one of the numbers received is not passed onwards. So this means that this picture here shows you what goes on in such a situation. The pipeline is illustrated in this figure. A message passing program using an SPMD or master-slave approach is straightforward, especially since each pipeline process executes essentially the same code. We see from this that there is virtually no opportunity for a process to continue with useful work on one pipeline cycle after passing on a number, meaning type 3. However, a series of operations is performed on a series of data items, like type 2, and this leads to a significant speedup even on one instance of the problem. Results of the sorting algorithm can be extracted from the pipeline using either a ring configuration or the bidirectional line configuration. The latter is advantageous because a process can return its results as soon as the last number is passed through it. The process does not have to wait for all the numbers to be sorted. So the algorithm goes something like this. We have the right processor number is n I minus 1. Then you receive the number and store it, and then you have the loop going through to receive other numbers and compare until you run out numbers. and then if the number is not, then you send it on and you pass on to the other numbers. Now more numbers pass through a process as processes get nearer the master process. So great care is needed in programming to ensure that the correct number of sends and receives are present in each process. Process n-1 has no receives and 1 send to process n-2. Process n-2 has 1 receive from process n-1 and 2 sends to process n-3 and so on. It will be very easy to mismatch sends and receive, in which case you will get a deadlock situation. So how long does this all take? Well, assuming that the compare and exchange operation is regarded as one computational step, then a sequential implementation of the algorithm requires TS equals n-1 plus n-2 plus and so on to 2 and 1, and then so that gives you n times n-1 divided by 2 number of steps. As it takes n-1 steps to find the largest number, n-2 steps to find the next largest number using the remaining numbers and so on. The approximate number of steps is n squared over 2, obviously a very poor sequential sorting algorithm and unsuitable except for very small n because it's O of n squared. But the parallel implementation has an n plus n minus 1 equals 2n-1 pipeline cycles during the sorting if there are n pipeline processes and n numbers to sort. So each cycle has one compare and exchange operation. Communication consists of one receive and one send except for the last process, which only has a receive. This minor difference can be ignored. Therefore, the pipeline cycle requires at least tcomp equals 1, tcom equals 2 times 2 startup, t startup plus t data. Therefore, the total execution time is given by this formula. T total equals tcom plus tcom times 2n-1, which is the same as 1 plus 2 t startup plus t data times 2n-1. If the results are obtained by communications to the left through to the master, then the timing diagram you get is what's shown in this picture here. Of course, a real parallel program does not operate completely in synchronization, as suggested in these diagrams, because of the delays in the communication media and other variations. Now we go on to a type 2 example. A classical method of extracting prime numbers is the Eve of Eratosthenes, described by Eratosthenes of Cyrene more than 2,000 years ago. In this method, a series of all integers is generated from 2. The first number, 2, is prime and is kept. All multiples of this number are deleted because they cannot be prime. The process is repeated with each remaining number. The algorithm removes non-primes, leaving only primes. For example, suppose we want the prime number to go from 2 to 20. So we start with all the numbers from 2 to 20 as listed here in this first list of numbers. Then we delete the 4, 6, 8, 10, 12, 14, 16, 18 and 20, but that is the ones that we delete using 2. So we are left with this set of numbers. Then we start deleting the ones that are multiples of 3, and we end up with this set of numbers. So then we keep going on in this way. However, to find the primes up to n, it's only necessary to start at numbers up to square root of n. So all multiples of numbers greater than square root of n would have been removed because they are also a multiple of some number equal to the or less than square root of n. For example, if n equals 256 and square root of n is 16, it is not necessary to consider multiples of the number 17 because 17 times 2 would have been removed as 2 times 17 and 17 times 3 would have been removed as 3 times 17 and so on for other numbers beyond 16. Therefore, in our example, we have all the primes up to 20 by using only 2 and 3. Note that the basic method as described is not suitable for finding very large primes, which are the ones most interesting, of course, sequentially, because the sequential time complexity is significant and is dominated by the early passes through the list. A simple way to improve the performance is to consider odd numbers only. A sequential program problem usually employs an array with elements initialized to 1, true, and set to 0, false, when the index of the element is not a prime number. Letting the square root of n be square root n, we might have this algorithm as shown here, and the elements in the array are still set to 1 to identify the primes given by the array indices. Then the primes are found by examining the array for ones. And the number of iterations striking out multiple primes will depend upon the prime. Hence, the total sequence of time then can be given by this formula in pink. T of S is n divided by 2 minus 1 plus n divided by 3 minus 1 plus n divided by 5 minus 1 plus so on until n divided by square root of n minus 1. Assuming the computation in each iteration equates to one computational step. So that means that we have a time complexity of O of n squared. So this implementation is very inefficient in that the inner loop will strike out numbers that may already have been deleted by a previous number. In fact, each sweep needs only start at I squared rather than 2i, where I is the prime number. For example, considering multiples of 5, sweeps can start at 25, that means 5 times 5, as 5 times 2, 5 times 3, and 5 times 4 will already have been considered with previous prime numbers. Note that the early terms in the expression will dominate the overall time because there are more multiples of 2 than 3, more multiples of 3 than 4, and so on. So a parallel implementation based upon partitioning where each process strikes out multiples of one number will not be very effective. So in fact, the maximum speedup using this method is limited to about 2.83, irrespective of the number of processes that you use. Well, this method can only use a limited number of processes in a practical situation. So there are other ways this problem can be tackled. For example, each process could be assigned a range of numbers and strike out multiples in that range. So because of this, a pipeline implementation can be quite effective. First, a series of consecutive numbers is generated that feeds into the final pipeline stage. This stage extracts all multiples of 2 and passes the remaining numbers onto the second stage. The second stage extracts all multiples of 3 and passes the remaining numbers into the next stage, and so on. So this is illustrated in the picture at the bottom of this slide. There have to be as many stages in the pipeline as prime numbers, unless a block partition is used in which each process handles a group of numbers in the list. The pipeline implementation does not have the disadvantage of reconsidering numbers already identified as prime, as does the simple sequential version. So how do we do the code? Well, we could base it on this idea. We receive the prime number, and then you receive the other numbers, and if the other numbers are not divisible by my prime, then I send the numbers on to the next guy. Note that a simple for loop is not sufficient for repeating the action because each process will not receive the same number of numbers and the amount is not known beforehand. A general technique for dealing with this situation in pipelines is to use a terminator message which is sent at the end of the sequence. Then each process could be receiving a number and then we keep going, but if we find the terminator, we break out of the loop. By the way, note that the mod operator to detect whether a number is a multiple of another number is expensive in execution time, and we intentionally avoid its use in the sequential code. As with the sorting example, the pipeline implementation is a type 2. Analysis of the algorithm is similar to the sorting algorithm, except that each process in the pipeline will complete fewer steps than the preceding process because it will not receive all the numbers that the preceding process receives. So how does the back substitution work? Well, first the unknown x0 is found from the last equation, x0 equals b0 divided by a00. Then the value obtained for x0 is substituted into the next equation to obtain x1 as x1 equals b1 minus a1 0 x0 divided by a1 1. Then the values obtained for x1 and x0 are substituted into the next equation to obtain x2, where x2 equals b2 minus a2 0 x0 divided by a2 1 x1 divided by a2 2. And so on until all the unknowns are found. Clearly, this algorithm can be implemented as a pipeline. The final example is type 3, in which the process can continue with useful work after passing on information. The objective here is to solve a linear system of equations of the so-called upper triangular form, which looks like what is shown in the pink here. So the a's and b's are constants and the x's are unknowns to be found. The method used to solve for the unknowns x0, x1, and so on is a simple repeated back substitution. The first pipeline stage computes x0 and passes x0 into the second stage, which computes x1 and from x0 and passes both x0 and x1 to the next stage, which then computes x2 from x0 and x1 and so on, as shown in this diagram below. Each stage is implemented with one process. There are n processes for n equations. That means p equals n. The ith process, where I is between 0 and p, receives the values x0, x1, x2, x3, and so on until xi minus 1, and computes xi from the equation as shown in pink here. Xi is the summation, is bi minus the summation of from 0 to I minus 1 of aij, xj, divided by aii. Here's an example for the sequential code. Given the constraints a, ij, and bk stored in arrays a and b, respectively, and the values for unknowns to be stored in the array x, the sequential code then looks like what is shown here. You have x sub 0 equals b sub 0 divided by a sub 0, 0. Then for I to n, this is for the remaining unknowns, we get the sum and then we loop and calculate the sum for the aij times xj, and then xi is then bi minus the sum of the divided by aii. Now let's look at the algorithm for the pipeline version. So for the ith process between 1 and n, you have the loop j equals 0, j less than I, and then receive from the previous process the xj's, and then we send on to the next process. So the next process can then get started while we are doing our own sum here and our own loop here and calculating our own x sub I and send that on to the next process. So this means that the next process can start computing while I'm not done yet. So as it states here, we have some additional computations to do after receiving and resending values, and we will see that in a couple of slides later from here. Another way of doing it is as shown in this slide, where you have the sum is initialized, then you receive and you send, and then you do the sum. And then after that you will calculate yours and you send. And this way the process can compute the sum and does not need to wait for the second x value before he can proceed. Here's the timing diagram that I mentioned earlier. You see how process 0 passes the first value onwards, while then process 1 can get started while process 0 finishes up, and meanwhile process 1 passes the value on to process 2 and it keeps going, and process 2 can get started, and so on until you get the final computed value at process 5. How long does this all take? Well, for this pipeline, we cannot assume that the computational effort is the same at each pipeline stage, as we saw in the previous timing diagram. The first process P0 performs one divide and one send. The ith process between 0 and P minus 1 performs I receives and I sends. I multiply, add, 1 divide, subtract, and a final send, and a total of 2i plus 1 communication times and 2i plus 2 computation steps, assuming that multiply, add, divide, and subtract are each one step. The last process P sub P minus 1 performs P minus 1 receives, P minus 1 multiply, add, and 1 divide, subtract, a total of P minus 1 communication time and 2P minus 1 computation steps. So, the operations in which the communication time and combine, multiply, add, or divide, subtract are the same. So in that case, we get a perfect synchronization of the sends and receives, and the parallel execution time will be given by the final process plus P minus 1 sends plus 1 divide to compute x0. So, in essence, the parallel implementation has an O of n time complexity as P equals n. The sequential version has a time complexity of O of n squared. The actual speedup is not n, however. It would depend heavily on the actual system parameters. We would expect a computational step, even division, to be much faster than the time of a communication step. To reduce the overhead of communication, we could have applied non-blocking send routines to allow the source process to continue as soon as possible with the next computation. The processes will in general be constrained by the blocking receives. So we have studied how to parallelize the solution of a set of linear equations having upper triangular form, which also applies to a set of linear equations having lower triangular form. Such equations do occur in practice, and for solving the currents for example, for solving the currents in an electrical circuit consisting of resistors and voltage sources. More important, however, back substitution is an essential component of solving a general set of linear equations when using Gaussian elimination. So Gaussian elimination converts a set of linear equations into triangular form, after which back substitution is used to solve the equations. So in summary, this lecture introduced the pipeline concept and its application areas, an analysis of pipelines, examples illustrating the potential of pipelining, including insertion sort, prime number generation, solving an upper triangular system of linear equations. So pipeline processing is most often seen in specialized very large integration components, VLSI, designed to implement arithmetic algorithms. Apart from the simple one-dimensional pipelines with data entered at one side only, more complex pipelines or linear arrays can be devised in which the data is entered from the left and right simultaneously and information moves in both directions. Also, two-dimensional arrays can be devised, especially for implementation in VLSI. So hopefully now you have an idea of how to implement in parallel things that are not so obvious as they were in the previous lecture.